why the need for mathematical induction? Well, we use this example to explain how mathematical induction can be used as a method of proof. So suppose we have a property n plus n equals to 2 times n for all integers n greater equals to 1. Now this is a simple property. One look you know that this is a true property because we are saying that if you have any numbers, if you were to add them together, it's as good as multiplying the number by 2 and they will be equal. So but how do you go about proving this? So our aim is to prove that the property is true for all integers n greater equals to 1. So I will start by showing you the wrong method. Okay, to attempt to prove that the property is true by substituting successive values of n. So we say, okay, you want to prove that the property is true for n greater equals to 1. I will start by proving that it's true for n equals to 1. So when n equals to 1, I substitute n equals to 1 into the left hand side of the property and to the right hand side of the property. So left hand side I have 1 plus 1 equals to 2. Right hand side I have 2 times 1 equals to 2 as well. And then I say, okay, since left hand side equals to right hand side, the property is true for n equals to 1. Okay, then I proceed to show that the property is true for n equals to 2. So when n equals to 2, left hand side equals to 2 plus 2, which is 4. Right hand side is 2 times 2, also equals to 4. So I conclude that, okay, left hand side equals right hand side, property is true for n equals to 2. Okay, I can continue to do this for n equals to 3. So left hand side will be 3 plus 3 equals to 6. Right hand side 2 times 3 also equals to 6. So property is true for n equals to 3. Okay, continue, do for n equals to 4. So left hand side 4 plus 4 equals to 8. Right hand side 2 times 4 also equals to 8. So property is true for n equals to 4. Now there's a problem because we can continue doing this for the rest of our life. Okay, and still we will not be able to prove that the property is true for all integers n greater equals to 1. Okay, so instead our constructed proof, we can only convince people that property is true up to the value where we stop. So we can't reason for sure that the property will be true for all other values which we have not worked out. So what is the solution? The solution for this is to use mathematical induction. Okay, the reason is because mathematical induction provides a generalizable proof. So we will follow the method and see how we can prove the same property, but this time using mathematical induction. So recall that the steps is we will start by identifying the property that we are trying to prove. Then we prove that the property is true for the initial term, and then after that we pick a value k. Okay, assume that the property is true for pk, and we proceed to prove that if pk is true, then the next term will be true. That means the property will be true for pk plus 1. So property that we are trying to prove is n plus n equals to 2n for integers n greater equals to 1. So we identify the property. Property pn will be n plus n equals to 2n. So we are done with step 1. Okay, it's one of the simplest steps. Okay, so there's a note here. P stands for property, and n represents the value to be substituted into the property. So when we say P4, we mean that n equals to 4. Okay, to be substituted into the formula. So P4 actually refers to 4 plus 4 equals to 2 times 4. Okay, so we use the shorthand Pn to represent property for value n. Okay, so we have proven Pn. Okay, next step is to prove that the property is true for initial term A, PA. So our initial term is 1 because n greater equals to 1 is where the property is true. So to prove PA, or in other words P1, okay, we start the value n equals to 1 into the left hand side. So 1 plus 1 equals to 2. That's for using the left hand side. And then do the same for right hand side. We change all the n to 1. So we have 2 times 1 equals to 2. So conclusion, since left hand side equals right hand side, P1 is true. So step 2, we are done. Okay, we have proven that the property is true for the initial term. Okay, so the value A in this case represents the first value for n in which the property is supposed to be true. So in this case, we say property is true for n greater equals to 1. That means our initial value is 1. So since property Pn is n plus n equals to 2n for n greater equals to 1, first value is actually n equals to 1. So that's why we need to prove that P1 is true. So we are done with step 2, so we can proceed to step 3 now. Okay, step 3 is to assume that pk is true. K does not have a value. K is just representing any possible value. Okay, so pk is true. We assume pk is true, so substitute, change all the n to k. So we have k plus k equals to 2 times k. So and we assume that this is true. Okay, so step 3a, we are done. Okay, step 3a is the simplest step in the entire mathematical induction process, because what we are doing is basically we are assuming that the property is true for n equals to k, and we just basically change all the n to k. That's it. So as we are making an assumption, there's no need to prove that left hand side equals to right hand side at this step. Okay, the next step is to prove that pk plus 1 is true. Okay, in other words, prove that the property is true for n equals to k plus 1. So left hand side, we substitute n equals to k plus 1 into left hand side. So left hand side is n plus n, right? So it becomes k plus 1 plus k plus 1. So we rewrite that, okay, to be put all the k together. So we have k plus k equals to plus 1 plus 1. Okay, so k plus 1 plus k plus 1, we change to k plus k plus 1 plus 1. Okay, k plus k is 2k, 1 plus 1 is 2. So left hand side we have 2k plus 2. Okay, and the right hand side we substitute, change all the n to k plus 1. So we have 2 times k plus 1, okay, which gives us 2k plus 2. So as you can see, the left hand side and the right hand side, they are equal. So property pk plus 1 is true. Okay, so step 3b, we are done. So notice that the working for the left hand side, we actually made use of our assumption in step 3a, where we work out k plus k equals to 2k. So we are talking about this part here. Okay, we are using the assumption, okay, k plus k equals to 2k over here. So it may not seem crucial at this case, in this particular proof, but actually this is an important strategy in mathematical induction. We will be using it, okay, for all our other examples. Okay, so as a conclusion, let's recall that what we have proven. We have proven that property P1 is true. Okay, the property is true for n equals to 1. This is the basis or the foundation step. We have also proven that pk plus 1 will be true if pk is true. We assume pk is true, and then we proceeded to prove that pk plus 1 is true. So this is the inductive step. With these two proofs above, okay, we can now reason that the property will be true for all integer n greater equals to 1. Why is that so? Because k can be 1. Okay, so when k is 1, 1 plus 1, okay, p2 will be true. Okay, k can also be 2. So when property is true for 2, okay, we know that it will be true for 2 plus 1, which is 3. Okay, and so on. So k can be substituted using any value, and we can prove that the subsequent term will be true. Okay, so suppose k equals to 1. So since p1 is true, we have proven this in our basis that p2 will be true, because if k equals to 1, k plus 1 will be 2. Okay, now suppose k equals to 2. Since p2 is true, proven in our previous step here, okay, p3 will be true, because if k equals to 2, k plus 1 will be 3. Okay, and suppose k equals to 2, since p3 is true, proven in the previous step, p4 will be 2, so this should be 3. Okay, so because if k equals to 3, k plus 1 will be 4, and so on. So we have actually came up with a generalizable proof, okay, a proof that we can use to build upon the values of n. Okay, so remember the domino effect in the analogy.